Okay, so we're gonna be doing some application problems. Today they're specifically cost and distance, but I wanna take a different approach to them. Part of what we need to do in this class is problem solving. And that means using whatever you have in your toolbox to come up with a solution to a problem. So, whereas traditionally, we would be talking about how to set up equations for this and solve these equations and figure out the value of the variables and then, turn that back into money or whatever the word problem happens to be talking about, we're going to forego that. Now, that does not mean that you can't do it that way. If that is the tool that you choose to use, that will be what you learned in Algebra 1 when you did systems of equations. For example, if we take a look at example 1 here, it says the cost to attend a play is $5 for kids' tickets and $6 for adult tickets. The total number of tickets sold was 30 and $170 was earned. How many of each type of ticket was sold? So this is the question they're asking us. How many of each type of ticket was sold? That means we have two unknowns, the number of adult tickets and the number of kid tickets. That would represent our variables. So we would start by saying A is equal to the number of adult tickets. K is equal to the number of kid tickets. Now, each kid ticket sells for $5. That means kid ticket sales would be $5K, $5 for each ticket. Adult ticket sales would be 6A, because it's $6 for each ticket. Combined, 5K plus 6A would be a grand total of $170, because that's how much total was earned. Now, the problem that we have is there are two variables in this equation, and we know that we can't solve an equation with two variables. Now, typically, we would look for some sort of comparison to get rid of one of the variables, but there is no comparison here. Instead, we just know that the total number of tickets sold was 30. That means K plus A has to equal 30. And what I have right here now is a good old-fashioned system of equations, which again goes back to Algebra 1. If you remember that and you like that, great. However, I want to talk about alternative methods for solving these. So what we're going to do here is we're going to be logical about this. We know that we sold 30 tickets. All right, so what we're going to do is we're just going to simply make a chart. Kids, adults, total sales. Now, kids' tickets are $5 each. Adult tickets are $6 each. If I started by guessing, you know what? Let's assume all 30 tickets were given to kids. That's $5 each. So that means we have 0 adult tickets, and that would give us a total of $150 in sales. Now, that's not enough money because we have $170 in sales. So that means we need to sell some adult tickets. Well, every time I sell an adult ticket, that's one less kid ticket. So let's go like this, and let's just drop and say 29 kid tickets times $5 each, 1 adult ticket times $6 each, and if I multiply this out, 29 times 5 gives us $145. 1 times 6 is 6. That makes a grand total of $151. So we're moving in the right direction. 151 is closer to 170 than 150 is. What if we did 2 adult tickets times $6? That would mean 28 tickets were kids times $5. That would give us a grand total of $152. Now, obviously, I can extend this table and keep going until we get $170 here. But let's just try to notice what's happening. Every time I add 1 ticket to the adult and take 1 away from the kids, my price over here increases by $1. When I made 2 tickets, it increased by another $1. So our goal is to get to $170, which means I would have to jump from 150 to get to 170. I have to jump by $20, which means I would have to have 20 adult tickets, which means there'd only be 10 tickets left for students. And the best part is I can easily check my answer. 10 student tickets times $5 each is $50. 20 adult tickets times $6 each is $120. And 50 plus 120 gives us $170. And again, 10 tickets, 20 adult tickets, that's 30 tickets total. So our final answer for the question is we sold 20 adult tickets, 10 kid tickets. Let's take a look at example 2 here. Now, example 2, suppose Ken has 5 more nickels than dimes and has a total of $1.75. How many of each coin does he have? Now, unlike number 1, we knew that there was a total number of 30 tickets. We were able to just make a table and say, okay, we have to have 30 tickets, so either it's going to be 30 kids and 0 adults, or 29 kids, 1 adult, 28 kids, 2 adults, 10 kids, 20 adults. And we were able to make a very straightforward comparison and see what resulted from that. But example 2, we don't know how many total coins Ken has. So we're going to have to think of it differently. So imagine we have a jar of coins that we just dump out. And we have a big pile of coins on the table. Now, if we're going to count the coins, it's going to be good for us to sort them out. So we could sort them out a few ways. I could try to sort all the nickels together and all the dimes together. But again, I don't know how many nickels I have and how many dimes I have. So instead, we're going to try it sorting in a different way. We're going to put together a nickel and a dime. Okay? And then we'll put together another nickel and another dime. And another nickel and another dime. And another nickel and another dime. Now, I don't know how many times I'm going to be able to do that. But I do know that when I'm done pairing things up, nickels and dimes, I'm going to have 5 more nickels left over. So I'm going to have all these pairs here, then I'm going to have an additional 1, 2, 3, 4, 5 nickels. And I know that all this money together has to become a total of $1.75. So let's see what we know for certain. We know for certain that these coins right here, those 5 individual nickels, make up 25 cents. We know that this pair of nickel and dime makes up 15 cents. This pair of nickel and dime makes up 15 cents. This pair of nickel and dime makes up 15 cents. This pair makes up 15 cents. Now I'm adding these all together. I don't know how many more pairs there will be. But I do know that when I add up all the pairs of nickels and dimes, plus just the plain nickels, again, that total has to be $1.75. So if we just take away this 25 cents, because we know that that's nickels, that means we have to have $1.50 from these nickel dime pairs. So each pair of nickel and dimes is 15 cents. So how many 15-cent pairs will make up $1.50? Think about it for a second. 15 cents. To get $1.50, we need 10 pairs. So that means we have 10 nickels, 10 dimes that are paired up, plus 5 extra nickels. That gives us a total of 15 nickels, 10 dimes. And the best thing is, these are super easy to check. If I have 15 nickels and 10 dimes, well, that's 15 nickels times 0.05 cents. That equals 75 cents for nickels. If I have 10 dimes times 0.10, because they're worth 10 cents each, that equals $1. And when I add my nickels and dimes together, I get $1.75, which is what we were supposed to get. All right, distance problems. So we have this very popular equation, D equals RT. It stands for distance equals rate times time. Pretty straightforward. I mean, if somebody's going 50 miles per hour and they're driving that way for 3 hours, they would go a total distance of 150 miles. Okay? Pretty, simple equation. So let's take a look at the situation that we have for this problem. It says 2 taxis leave an intersection at the same time, traveling in opposite directions. So I'm gonna just draw a picture using my lovely artistic skills. Let's see, we'll do a red car, a red taxi, and we'll do a blue taxi. The red taxi is traveling in this direction at 40 miles per hour. The blue taxi is traveling in the opposite direction at 60 miles per hour. Now we know exactly how fast each car is going. There's no questions there. We know they started at the same time. So let's just try making a chart. Taxi number 1, taxi number 2, total distance, and then let's add time. We know taxi number 1 drives at 40 miles per hour, and taxi 2 drives at 60 miles per hour. We know that the distance is rate times time. So if we start with 0 hours, okay, 0 hours times 40 miles per hour is a distance of 0 miles. 0 hours times 60 miles per hour is a distance of 0 miles, for a total distance of 0. So what we've just determined here, oh so nicely, is that at time 0 hours, in other words, before the cars start moving, they are 0 miles apart. Now let's take a look at what happens at 1 hour. So remember, our formula is distance equals rate times time. So 1 hour is the time, 40 miles per hour is the rate, so rate times time gives us a distance of 40 miles. For taxi 2, rate times time would be 60 times 1, which is a distance of 60 miles, for a total distance between them of 100 miles. Now we're looking for them to be 300 miles apart. So let's try 2 hours. At 2 hours, again, our formula, rate times time equals distance. So rate, 40 miles per hour, times 2 hours, multiply those together, and we get a distance of 80 miles. Same process for taxi 2, 2 times 60 is 120 miles, for a total distance of 200 miles. All right, what we should notice here is on this side here, every time I do another hour, this changes by 100. So if I were to do one more hour, this would change by 100 and we'd be at 300 miles. This would be 3 times 40, which would be 120, and this would be 3 times 60, which is 180, and 120 plus 180 does equal 300 miles. So the question says, after how long will they be 300 miles apart? That would be 3 hours. All right, and example 4. It says, Vicky and Caroline are on their bikes and leave an intersection at different times, traveling in the same direction. Vicky's rate is 5 miles per hour, while Caroline's rate is 3 miles per hour. If Vicky leaves 30 minutes after Caroline, how long will it take for Vicky to catch Caroline? So imagine a starting point, and we've got Vicky's bike, and we've got Caroline's bike. This is at time 0. Now we know that Vicky is going to ride at 5 miles per hour and Caroline is going to ride at 3 miles per hour. So now let's look 30 minutes from now. 30 minutes from now, Vicky is still sitting at the start line. Caroline, however, is been pedaling for a while. How far has Caroline gone in that 30 minutes? Well, again, let's remember our formula. Distance is equal to rate times time. So to figure out Caroline's distance, her rate is 3 miles per hour. Her time is 30 minutes. Now we have to be careful. 30 minutes is measured differently than hours. So we have to say 30 minutes is really 1/2 of an hour for time. So 3 miles per hour times half an hour gives us 1.5 miles. Now, at some point in time later, Caroline's going to be up here. And Vicky is also going to be up there. Because Vicky is moving faster than Caroline. So Vicky is going to eventually catch up to her. The question is, how much time will it take for Vicky to catch up? And the way we could figure that out is to take a look at the difference between them. Vicky is 2 miles per hour faster. That means every hour, Vicky will make up 2 miles. Well, how much does Vicky have to make up? 1.5. So Vicky needs to make up 1.5 miles, and she's doing it at 2 miles per hour. So in 1 hour, she'll have made up 2 miles, but she doesn't need to go that far. She just needs to make up 1.5. So what we could do is we could take 1.5 miles divided by 2 miles per hour, and we find out that it takes her 0.75 hours, which, if you prefer, is 45 minutes. So how long will it take Vicky to catch up to Caroline? It will take Vicky 45 minutes.